we are going to talk about carbon drawdown now. I really like the fist raised. And how we all here collectively can turn our buildings into a carbon sink. We're going to be working kind of with two levels. We're going to talk about a simple, kind of straightforward message, and then we're going to talk about something a little bit more life cycle engaged. So the simple message that we're going to sort of frame our talk with is that making carbon storing buildings is the most important action that the building industry can take to address climate change right now. The life cycle message, which is a little bit related and deeper, tells us that if we actually truly are going to address the particular issues that have arisen in our decade, in this time, we are going to have to change our thinking and move beyond narrow and mechanistic views into a more interconnected style of thinking.
Following from that, sort of the look at climate change itself has that same two-level kind of viewpoint. The simple look at climate change, what is climate change? Well, it's too many greenhouse gases in the atmosphere, and you can peg a number to that right now, about 411 parts per million. But the larger life cycle message is that it's been our sort of single-minded pursuit of a fossil fuel economy at the expense of sort of everything else that has got us here. So we can't just think about climate change as a mathematical problem of too much carbon in the atmosphere. It's a societal problem of how we have gotten to this point where we put that much greenhouse gas in the atmosphere.
We must drastically reduce the carbon being emitted from our buildings within a decade. So that is the simple message. We have a very short window of time in which to dramatically pull down the emissions coming out of our buildings. But it's a lot more complicated than that. The material substitution approach and just simply swapping out materials and continuing our practices as business as usual is not going to get us there. That is not going to be the path. And we need to look beyond our small silos and our small little rooms as professionals and branch well beyond that and work in a much more connected and multidisciplinary, multi-industry fashion to be able to actually achieve that goal of reducing the carbon emissions of our buildings. That means partnering with forestry, partnering with agriculture, and partnering with those that are working really hard to promote forward action in social and climate justice.
All right, and as Michelle really well set us off thinking about, in order to think about climate justice, which is the thing that we want to move forward with, the positive vision, it is really helpful to name what is unjust or what is unjust about what we currently have. So the utility of naming that tells us that actions by the few affect the many. That's a really great situation, right? For fairness, like it's not often true that that's a good scenario for fairness. And then additionally, no accountability or recourse for the many that are impacted by the actions of the few. So that is the situation that we are going to right and change. So climate justice says that we need to reconnect people across the socially reinforced divides that exist for our common cause and for our common resource and planet and the place we live. Create that accountability and build political power to redirect resource control to the many. How many folks have heard of Soul Fire Farm? They're based in New York. Oh, that's good, a couple few. Excellent. Anybody who doesn't know their work, highly recommend checking them out. So this is Leah Penniman here in the photograph. And she's one of the founders of Soul Fire Farm. And she just published a book, which I actually brought to show, because it's very beautiful. It just came out. It's called Farming While Black, which is awesome, reference to driving while black, but a positive spin on it. And basically, she's writing about the way in which engaging with the land in a new way promotes healing, especially in the wake of violence that has happened on the land, particularly around race and colonialism. So this quote, which I love, organic matter in the soils on the plains, and that's in the United States, plummeted by 50% in only one generation of white settler colonialism. Leah says, I realized that all our efforts to heal the soil entailed the restoration of organic matter and was, in effect, a decolonization of the soil. We are inviting our non-human relations back onto the land and back into relationship with us. So On the left, the three of us are going to stand here and say to all of us that we see carbon action around our buildings as an opportunity to decolonize our industry. So we're going to just take a second to talk about soil. And I know all of you are like, hello, we're in a building conference. Why are we talking about soil? But the reason that we are is because soil is actually a critical connector to what we're about to talk about. So the soil is a place that is a meeting place between the lithosphere of rocks and stone and the organic biosphere. So quite literally, soil is a mixture of those two things: sand, clay, silt, and organic matter. And it is essential, obviously, for the food that we eat and many of the building materials that we use, and certainly the building materials that we will be talking about. So quickly here, I really like this image. It helps me understand the ways in which carbon cycles through the multiple spheres of the Earth. So yeah, I know. You mean as a builder or designer I need to understand Earth science? Yeah, probably. So we're here to say even just a little bit we're going to need to do to understand why our actions need to be what they need to be. So we're going to talk about particularly this little teeny wedge of this big pie, right? Michelle mentioned the oceans earlier in the introduction. So we are going to talk about the pedologic, which is sort of the soil and stones, and then the biotic, which is plants and animals. So I mentioned it before, but you can count 5 here, right? So this is what's called the fast carbon cycle. There are 2 carbon cycles, a fast and a slow. The fast deals with like very short time frames, like 1 year or like every hour daily, you know. Things get, the carbon is moving through these particular sections. In the slow carbon cycle, we're talking eons. We're talking sort of volcanoes and tectonic plate movement kind of times. So both of those are critical and important to the Earth's carbon cycle. But what we're going to talk about is what we can do in the fast carbon cycle to help bring that balance back, that climate change is a symptom of that balance being off. So these 5 that you see here, these carbon sinks, we are going to make our buildings the 6th carbon sink.
So we want to get some definitions of terms in place here when we're talking about carbon and carbon emissions. We want to talk about embodied carbon and what we mean by that compared to operational carbon. So operational carbon are the emissions that come from our buildings as our buildings are being used. Heating, cooling, lighting, plug loads, generally energy-based emissions. And so we want to look at the embodied carbon of our buildings. And in this case, it requires us to take a complete life cycle view. Again, bringing back that concept of not just looking at our buildings within this very narrow window of time in which they serve as a product that we create, but looking at the entire life cycle of what it takes to bring that building into existence, from the extraction of the materials out of the ground all the way through to their disposal and everything that happens in between. And so you can see by this little graphic here, there's a number of different periods and phases throughout the life cycle of a building. At any point and during every point, there are emissions that we need to try to be able to wrap our heads around how we manage those. So we're starting from extraction through manufacturing of materials, and then we get into the construction phase, and then our buildings operate. And so when we generally think about the carbon emissions of our buildings, and we're only thinking about the operational emissions, it's just that one little circle in the bottom right-hand section of this whole life cycle. When those buildings are then decommissioned, some of that material gets recycled. There's usually an emissions profile there. And then some of those materials get disposed, and there's impacts there as well. So you could look at the embodied carbon emissions of a building in its total life cycle analysis. And that is totally legitimate and a very valid perspective of analysis to understand the impact of our buildings. For the purposes of our conversation, we're just going to be looking at what's called the cradle to gate. And we're looking very specifically at what it takes to get our buildings into existence in the first place. And a lot of that is looking very specifically at materials. So we're going to be focusing a whole lot on materials over the course of this conversation because that is the first immediate release of significant amounts of carbon emissions during the course of the work that we all engage in. And as we learned, and as many of us know, and it was already stated in the beginning comments, we have 10 years. We don't have a luxury of time to work here, so we have to look at the points of time in this life cycle in which our emissions are happening immediately, and that is during this initial materials-based manufacturing and extraction and manufacturing phase. So that's why we have the red circles highlighted there. That is going to be our definition for the sake of this conversation of embodied carbon when we use that term. And again, carbon itself is actually not a super accurate term. So we're using that as kind of a sort of shorthand word for carbon dioxide equivalent. So you're going to see CO2e, and that's going to show up on the screen again and again. What we mean, we're not talking about carbon like the individual molecule carbon. Carbon is usually shorthand for carbon dioxide. But carbon dioxide is not the only greenhouse gas that we're worried about. There's a host of different chemicals, methane, all sorts of propellants and refrigerants that have a really large climate impact. And so the way we account for that and kind of normalize the impact of all those different chemicals is to make them all equivalent to the value of carbon dioxide. And so when we're looking at all these numbers of the amount of embodied carbon, what we mean is the embodied carbon dioxide equivalent of all the greenhouse gases normalized to a single value. So I just want to make sure we're super clear. When we just say carbon, we mean carbon dioxide equivalent. And when you see CO2e, that little e means equivalent. It's talking about all greenhouse gases. And if you see E, CO2e, that's embodied carbon dioxide equivalent, and O, CO2e, is operational. You don't have to hold all that now. We'll go over it again. We're going to see more of those. But I want to make sure we said this once. We'll say it 3 times over the course of the entire presentation. And the language is really important. These concepts are complicated. There's a lot to talk about, and so we want to try and be as clear and specific with the language as we can. Okay, that's enough of that. So let's look at this a little bit more, because I think we're very used to only talking about the operational side of things, and I want to invite us all into thinking and holding that embodied side, that before the building is a building part of the pie. And looking at this chart here on the left, we're looking at the total global CO2 emissions by sector in the US. And the buildings takes that sort of the blue and the green wedges of the pie to the right there. The blue is the building and operations, that operational phase of heating and cooling and lighting. And the green is the materials and the construction, that cradle to gate, early phase embodied carbon emission. So that's the embodied and the operational. Now we're looking at this little wedge of green. Why are we so obsessed and focused on this very small part of the wedge? What's not shown in the pie chart on the left is the fourth dimension of time. And that is critical. What we know is we have 10 years, 12 years to change the trajectory of our emissions profile. And what we know looking to the right, when we start examining when those emissions are happening, we see there is a tremendous front loading in time scale of the building's carbon dioxide equivalent emissions during that initial phase of material extraction and manufacturing. And so we have not only an opportunity, but a mandate to address the building's emissions from those early phase releases, from the embodied side of things. The operational emissions, they accumulate year after year after year after year as the building's being heated and cooled and lit year after year after year. But we cannot take an incremental approach to solving this problem. That ship sailed a generation ago. Our approach has to be immediate. And the time scale of intervention to take immediate action is in the materials and is in addressing the embodied carbon dioxide equivalent emissions of our structures. And so that time piece is critical. And that's why we cannot net zero energy our way out of this problem. That is an absolutely laudable goal. We have to have net zero energy buildings. I am not disputing that in the least, but that is simply not enough. It will not get us to the goals that we need to stabilize the temperature of this planet.
From that sort of big picture piece, what we've been working on is sort of now breaking it down into the level of the materials themselves. And we'll show you the case study buildings we're using, but this is just a snapshot from that case study of actually looking at individual material types and what their emissions associations are. And so you can sort of see, don't get too hung up right now on what that material is and what the number means, but you can see that there's a range. Some things emit a whole bunch there's a lot of embodied emissions associated with them. Some have less. And then there's this very interesting one that's green and going kind of like the wrong direction on the, on the graph. And it turns out that the wrong direction is kind of the right direction. So what that wrong direction, what that negative number means is that the physical property of that material, it's a plant-based material, in this case it's hemp-based, has atmospheric carbon dioxide in its structure. It's a plant, it drew CO2 out of the atmosphere to build itself, and so about half of the weight of that plant material is, or was recently, atmospheric carbon. It's taken it out of the atmosphere and we've put it in the building, and that number of the amount that it's storing is greater than the amount that went into planting the seed, harvesting the seed, processing the material. So in a net version, it becomes a carbon storing material. If you put it in your building, you're actually drawing emissions down rather than creating emissions.
Yeah, so Chris really quickly was like, this is how this works, which, you know, a lot of us can just go back to, I don't know what grade, of learning about photosynthesis. I think it might have been 8th for me, I don't know, but anyway. It's exciting to realize how plants are actually, I mean, huge heroes in many ways. You know, most of us eat because of them, and also breathe because of them, which is pretty key. And then, you know, additionally, what we can understand as builders is that during that photosynthesis process, as Chris was saying, gaseous carbon is drawn down into the body of the plant and fixed within the plant itself, and then also, interestingly, in the root systems of the plant, and then exchanged across into the soil. And the soil itself becomes a really significant carbon sink as well. So there are two things happening. The plants themselves are holding the carbon and storing it, and the soil is also being loaded with it because of the action of the plant.
Well, I was just going to say, I think it's interesting that, you know, if you look at what's going on in the climate science world now, there's a lot of time and money being invested in coming up with the machine that is going to pull CO2 out of the atmosphere and fix it in the soil. Like, you know, we're trying to invent these machines that will do this, and the planet is full of these perfect machines that already do it. It's being done on a really large scale.
Have people heard of CSS, the carbon storage solutions? That's what Chris is referencing, but it's this sort of like technology engineering idea of how we're going to, you know, replicate these natural systems that actually were doing that the whole time, and we could just do more of it. The thing that I was going to say is that there was an interesting study that came out of UC Davis in California in looking at the resilience of these systems, so understanding the way that the biotic, as I referenced earlier, so the grass here, and this is sort of a grassland we can imagine from the picture, versus a forest, how those two things that both store carbon very well, how each one performs when it's confronted with something disruptive like forest fires and droughts, etc. And one of the things that they found is that the grasslands, because of two reasons: one, that they are more rapid growing, grasses are, than trees, and two, because of the really deep and profound root structures that happen underneath and do so much exchange with the soil, that the grasslands actually were not only more resilient to drought and fire, but also you know, stored more carbon in these climate change scenarios that included a lot of weather disruption, which I just think is really interesting, because forests are a huge part and certainly very important, but also interesting to think about different plants and, again, the time scales, which we've been talking about being really important as well.
So as a quick introduction to the notion of plants as building materials, these are just some examples of the things that we've worked with, that are out there, that people work with in different parts of the world, all of which are carbon storing and quite feasible building materials. And I think, you know, of particular interest in this talk is looking also at waste stream materials, so not just you know, new plants, but plants that we've harvested for other reasons and are now in our waste streams and can be pulled out and used that way. And as a sort of sub-note, the little note on the bottom of the screen, by and large when we use these materials, they don't have any weird chemicals in them. So as a sort of additional benefit to building with plant materials, in a lot of times you sort of really change the toxic profile of the building materials by switching to the plant-based ones as well. There's also some really, really interesting things going on with mineral-based carbon storing materials, and I think there's going to be sort of more action in this field as time goes on. But right now in the US, there's a company called Biomason, and they're making microbe concrete. So they have developed a strain of microbes that they put into sand, and they feed the microbes, and the microbes excrete calcium carbonate that glues the sand together, and you have microbe-generated concrete or bricks, have all the same properties, but done at room temperature, no waste, no CO2 emissions, and again, that carbon that is now the calcium carbonate came from the atmosphere and is fixed in that form. And then you have companies like Carbonate and Blue Planet who are doing that kind of large-scale carbon extraction, taking smokestack emissions, grabbing that carbon and catalyzing it in various ways and turning it into calcium carbonate, so limestone from waste emissions, and that can be aggregate for concrete. And I had a student at our school last year from Ghana who brought some really interesting bags of materials. He brought palm kernel ash and palm kernel shell. And palm kernel ash is really interesting. So it's burned to make heat and or power from the waste of the palm kernel. And that material is cement. And we were basically working with combining the palm kernel ash with the palm kernel shell as aggregate, and you get a lightweight, long-lasting cement that's entirely plant-based. So really interesting things going on the mineral side of things as well. All of these thoughts, all of these concepts about, you know, what can we do about embodied carbon emissions, what kind of materials do and don't work well that way. I got really excited about this 5-ish years ago, started doing some citizen science, kind of like poking into this myself, trying to look at, you know, how our buildings would stack up, how other types of buildings would stack up. And I got so into it that I went back to school and did a master's in it. So a lot of the sort of technical stuff that we're going to look at comes from that study. What happened in that study was we took 2 different building typologies, a sort of single family residence of 2,000 square feet and an 8-unit 4-story building. These aren't the actual buildings, but they're sort of representative of them. And essentially looked for all the materials for those buildings, built in a whole bunch of different ways, and sourced environmental product declarations for all of those materials. If you don't know what an EPD is, it's sort of, people call it a nutrition label for materials. So a company will hire a third party to do an EPD, and they review sort of all the energy and material inputs and outputs of somebody's entire process and come up with a bunch of figures. The one that we're looking at for this study is the GWP, which is the global warming potential. So that sort of puts all of these materials on a fairly even footing. They've kind of been looked at through the same product category rules, and you know, if anybody wants to talk about variations in product category rules, like, they're not 100% comparable, but they're the best numbers we have. And so for this study, the way we did it was sort of had a hierarchy of these EPDs that we used. So if there was an EPD that was for a North American average of a product type, that was our go-to sort of information source. If there was product-specific ones, so sometimes in a product category 3 or even 4 different manufacturers will have their own EPD. If that was our source, we found as many as we could and then we averaged them. If there were no North American numbers, we went to Europe. Same thing if there was an industry-wide thing or multiple products. If there were no EPDs, sometimes there are life cycle analyses of these materials done in universities to the same kinds of standards. So if we couldn't find an actual EPD, we would go to the source data, the LCA. And as a default, in a couple places where we couldn't find any of those other figures, there's a database in England called the Inventory of Carbon and Energy, and that was where the numbers came from. So just to sort of give you a background on how the numbers in this study were built, this is where they all came from. And essentially, this is the result. So the modeling was done basically using every material that it's possible to use in North America, and that makes for a lot of different model types. What we're showing you here are basically 4 models. So the red bar is, we chose the materials that simply had the highest embodied carbon in every category. And just as a note on that one, far from being a sort of academic exercise of like, oh, let's just choose the high ones. These are things that we use all the time. So included in here would be foam-based insulation, brick cladding. They're very normal materials. There are a lot of buildings being built like that red column. The blue column is, I tried to model a building as though it was being built as conventionally as possible in Ontario, Canada, where I'm from. So this is now switched to things like vinyl siding because it's cheap, and vinyl windows and those sorts of materials. The yellow bars are looking at the materials that you can go to any big box store right now and buy, but that have a really low carbon footprint. So these are sort of conventional materials that any of us could start building with right now. They're all code compliant, and you can buy them as products, and they're available in North America. And then the green bar is sort of the opposite of the red one. Let's just choose the best carbon storing materials possible. And in some cases, they're not things that you can go buy. They're things that people are building with, but they're not widely available. And so you can see, we also modeled them according to 2 different energy efficiency standards. So we would sort of build up the model of the building as though it was being built to code minimum energy efficiency, and then sort of improved energy efficiency version. And then there's the big building and the single family. So in order going across the screen, MF is multifamily, CC is code compliant, MF multifamily high performance, and then single family code compliant and single family high performance. And so right from this graph, and now these results are normalized to per square meter of construction, so that we can actually compare the bigger building to the smaller building.
And just a quick note, some of you may have seen some presentation on this work that we did last year, or read the article that we put in Building Energy. So we have updated this data. We've done a much more rigorous operational energy analysis. We went to a dynamic hourly modeling and included all of the operational components of the building. Chris did a whole bunch of updating on more current EPDs, and really sort of even up to this last month, there was a whole batch of EPDs that released at the beginning of the year. So this is the most up-to-date data we have. Also, what we had published was code minimum construction in Ontario, and we refactored all this information to be code minimum for the IECC minimum for Massachusetts, and using Massachusetts, Boston specifically, as the location for all the operational modeling. So this is updated to be more specific to us here today, and also incorporating the 8-unit building so we could get a little bit of a sense of how this changes by scale.
We're going to dive into those numbers in more detail shortly, but what I wanted to start with was just sort of showing what does this mean at any kind of scale. So, on the previous slide you can see there's high bars and there's low bars. Great, what do those numbers mean? So in the worst case scenario, if we built all our buildings to be, high performance buildings using the materials that made those big red bars, so at 345 kilograms per square meter, all the low-rise buildings, residential buildings built in the US in 2017 would mean that our buildings alone, the carbon footprint of just building the buildings is about 83 million tons of CO2, which is the equivalent of the output of 23 coal plants in 1 year. And that's just residential low-rise construction. So, the impact could be that big. The thing that we're here to tell you that's really hopeful is that the flip side of that, if we can switch over and build all those buildings in a carbon storing way, we would have put away 150 million tons of CO2, and that would be like taking 10 power plants offline. And if we can currently we are kind of doing the first scenario and we're not doing the second one. So there's, you know, the balance of like 33, you know, coal plants per year lying in the balance of, if we keep doing the red thing, you know, and doing the green thing, it's a huge thing. And that's really meaningful, I guess, for me in Ontario, because we took our coal plants offline 4 years ago, and you'll see what that does to our energy data later on, but it was the single biggest drop in emissions in North America ever, taking just 6 plants offline. So when we're talking taking, you know, potentially 10, 20 plants offline on an annual basis, you know, this work can have a really large scale impact.
Yeah, and so similarly on the kind of scale front, it's kind of, you know, often people will say, okay, so, you know, building with straw, that's weird. And it, you know, it is. And also it can be really normal. And I think we're here to sort of ask that we open our minds and think about things in new ways, because we need to. And, you know, how many, kind of scale-wise, how much straw do we produce globally, annually, to actually make an impact like we're talking about? And so 2.16 billion tons of grain straw were grown in 2016. And so, you know, as it says here, that is enough carbon storage to offset the transportation greenhouse gas emissions, and more than replace all current insulation materials. So is the question, do we have enough? What would happen? A lot of this straw is going to be a waste product, and it will either be burned or rot in the field. Now, there's another question of, we need to return minerals and nutrients back into the soil. That's actually a really important part of it. But when a plant rots or burns, it releases its carbon back into the atmosphere, which is the opposite thing of what we are trying to do. And so when the plant is put into a building and we keep it dry and we keep it you know, sealed from air and from any kind of decomposition, then that plant stores that carbon in our buildings. That is how that 6th sink of our buildings will work. And so these are just some examples then on the right there of products that are in use currently in our world that I really encourage everyone to look up. So the EcoCocon straw SIP panels, which are on the top right there. ModCell is another example happening in the UK. And then you can see Endeavour gets up on there, which is really great. So Chris and their school have done some buildings with them. And we as New Frameworks have been really encouraged by that and mentored by you guys. And we're actually going to be doing one this year, which we're very excited about. Formaldehyde-free straw panels, so these can replace, you know, drywall or other kind of wallboard products in the home. And then the blown straw insulation is another kind of next step of what we could be looking at. And again, remember when I was talking about the grasslands and how these plants are a shorter growing cycle and so can help us really pull a lot of carbon out? This is exactly what we're trying to look at in terms of utilizing these types of plants in our buildings. And just as a quick plug, we'll talk about it at the end too, but we're going to be doing a demonstration wall on Friday morning looking at exactly these types of things in a double stud wall, high performance wall, and encourage everybody to come by and take a look at some of those products and ask questions. We were just talking about, Chris went through looking at the embodied carbon data. We're going to now talk about the operational greenhouse gas emissions and how we need to look at them together. So, great. The embodied emissions that we just saw are pretty staggering, the difference between the types of materials that we're using in our buildings and the carbon emissions that do occur as a result of the embodied emissions in those materials. Now, let's also factor in the operational emissions. So Chris was referencing the changes that happened in the Ontario grid, and what we're going to look at now is the overall climate impact of our decisions as builders and designers and how those two together stack up. So, there's the bad news. That's okay, we can handle bad news, we just need to know what to do next. So again, looking at this 8-unit residential that Chris spoke about that was modeled, we are looking at a high embodied carbon equivalent building that is built to code compliance, and this is on the New England grid. What we see here is the yellow bar is the embodied carbon. So this is the amount that went into the building before anybody, turned the lights on, plugged anything in, started using the building. This is what is already the climate impact just from the, creation and, of that building, transportation, et cetera. The bar on the right here is the total carbon emissions after each year we see our operational energy impact, the greenhouse gas emissions from the use of the building, from the operation of the building. So those two things together have quite a significant, you can see it's basically doubled. And the time scale here we're looking at by 2050, 2051. So we're not going to be in good shape if this is the direction that we take with our large multi-unit buildings or our small single-family buildings. So there is good news, and we can do exactly the same thing with exactly the same building with different materials. And we can, now there's a couple of important things to note here, right? There's the approach of the building style that was the lowest embodied carbon equivalent materials used in the building. Also, it's still high performance, so that's really important to note. It is not a low performing building in terms of air tightness and efficiency or any of its mechanicals. And then we are also looking at it on the Ontario grid. So we've chosen to look at it with a cleaner grid than what the previous one was. So with those, and again, going back to our message of like the simple message and then the more like life cycle, why do we have to pay attention to these other factors as builders? Well, this is why, because these things really do impact each other quite significantly. So we can see here that we've, instead of being up here with our emissions, we're below the line. We have stored carbon, and even though there's incremental adding of operational emissions every year, we end up with still a really impressive net, net positive, really, of the building. And I think this is a really important thing for all of us to note, that instead of getting to do less harm, we get to actually consider that we could do really, really good. We could do this really cool thing for our planet and ourselves and our people, and that our trade could be that answer and that solution. So this building can be a drawdown building. I mean, really, this is kind of our core thesis here.
Yeah, it's a pretty astounding paradigm shift, to go from assuming that our buildings have to do some bad to the climate to actually considering that our buildings could be exactly like the large-scale drawdown thing, and that it lasts. If the grid is clean and the building is efficient, that drawdown, it's a pool. I forget when we extended that line out, but it's till like after 2100. The thing is still a net store. So it's doing that work over the kind of time scale that we really need to help address the state we're in right now.
We want to go through just highlight a bunch of points. Now, this is obviously super complicated. We're looking at 2 different types of buildings. We're looking at each of those different scales of buildings with different performance factors. We're looking at them with 4 different types of material profiles. We could spend a very long time digging into all of this, and we just want to highlight a couple of key sentient points here. And so we're going to kind of put all this together in one graph. I want to explain what's going on here. So again, we're looking at, this is for an 8-unit residential building, the big building, using natural gas for heating, high efficiency natural gas for heating and hot water, and the rest of the electric loads on the New England grid. We're looking at the high, when we say high, mod, low, and best, those are the different types of embodied carbon profiles of the materials, like Chris was describing. So the highest amount of embodied carbon, all the way down to the best carbon storers. And again, CC is code compliant, and HP is high performance. So in each of those, we're looking at the code minimum and the high performance versions of those. The red bars, or the green bars, if it's a storer, is the embodied carbon, and the yellow is the operational carbon. And so you're going to start seeing, as we click through, the E CO2E, that's for embodied, and the O CO2E, that's for operational. We'll continue to define that. We're just trying to help kind of make all the glyphs and the concepts kind of stick here. Are there any questions about this?
Yeah.
Yeah.
How many years of operation is that?
This is between now and 2050, or 2051.
2051.
And we're pegging that because everything that we have heard from Architecture 2030 and from the IPCC is that we need to have a truly net zero carbon industry by 2050. So that is the time gate by which we are bounding our analysis, because beyond that, this may not matter. Okay, so the first thing to point out is the high-performance building with high embodied carbon materials, ECO2e materials, releases more emissions than a code minimum building with moderately embodied carbon emissions. This is a really big deal.
It's a really big deal.
We cannot simply chase energy reduction and expect that we are doing good by the climate. Energy is not the same as carbon. And if we're concerned about our climate impact, we have to look at carbon emissions. We cannot just look at energy consumption. We recognize this is pretty disruptive, and I also recognize, I want to invite all of us that have been spending our careers looking at energy to open our arms and broaden our analysis to not just look at energy, but to actually look at carbon. Second point. A 65% reduction in the heating load and 35% reduction in the cooling load, which represents the difference between the code minimum and the high performance buildings that we modeled, was actually a relatively small carbon emission savings if we're not also looking at hot water and lighting and plug loads. For those of us that have been working in the high performance building world for a while, we know that at a certain point, a domestic hot water energy usage is significantly larger than our heating load even in cold climates. And so if you're not already you can't just look at the shell. We actually, for our modeling purposes, use the same sort of HERS standard consumption for lighting, plug loads, and domestic hot water for all the conditions. And we're just changing the enclosure. And what we found is that actually doesn't make as much of a savings in the operational emissions as we would like to see. This has to be comprehensive. You can't just look at, oh great, I have a high performance shell and I'm done. The total energy profile really matters. And that includes hot water, includes lighting, includes energy. So as you go through the sessions over the course of the rest of this conference, pay attention to those details because they really matter. It is also possible to build a net zero embodied carbon building using kind of off-the-shelf code compliant materials. That was really encouraging for us. You know, using actual wood, using cellulose insulation, using fiberboard products. Like, we can all access those. They're on the shelf. We can use them tomorrow, and you can get to a net zero carbon, embodied carbon building using those materials. And if you do a high performance building with those materials, the total emission profile, including operation up to the year 2050, is less than just the embodied carbon emissions of that high performance building using high embodied carbon materials like plastic foams, et cetera, et cetera. And that's huge. That means we're front loading 50 years worth of carbon emissions just in building this one high performance building if we're not conscientious about the types of materials that we're using. So that really matters.
Yeah, and just as a note, like as I was building these models, the one that we're looking at now, that little tiny low green bar, or in the single family, it's actually slightly above the line, but it's pretty close to a net zero building. Even though those results don't look spectacular because they're right at the zero line, that was one of the most encouraging things to me, was that this, like, everybody can leave this room today and go build that building. That was literally basically a switch to cellulose insulation and wood fiberboard cladding on the outside of the building, and some wood flooring and some wood cladding on the outside. That's it. Like, that is the sort of like revolutionary change that it took to go from buildings that were, you know, really high in their emissions profile to basically you could look at it as a net zero embodied carbon emissions. So there are, you know, literally no real barriers to, you know, achieving that. Whereas, you know, there are barriers to moving to the best case scenario that we'll sort of talk about, but that to me was like the most exciting result when that popped out. It was like, whoa, everybody can do this, and it's, you know, that in itself is a really remarkable achievement. So we have now switched to the same building, the large building, but now we've gotten off the natural gas for the heating, and we're using the New England grid and heat pumps. And I know that there's a lot sort of pegged on the use of heat pumps in terms of their potential impact to reduce the carbon footprint on the operational side. But what's interesting is that in the state that the grid is in here right now, switching that building from natural gas to heat pumps is only a 13% savings in the operational in the end right now. It doesn't mean it's not a good strategy, but it means that, again, it's not the solution. You know, you're not going to fix the climate problem by just switching to heat pumps without addressing where the energy to run those heat pumps is coming from in the first place. So,
and just to clarify, the little gray bars you see at the top, that was the natural gas operational. So we're sort of contrasting the drop in operational carbon between the last building and this building.
Again, you know, if we want to look at the sort of the best side scenario, so the little hatching on the bar on the right is if you you know, the yellow is the operational carbon, the green goes below the line, the hatched part is how much of the operational is sort of taken up by the storage of the materials. So by 2050, that best case scenario building has emitted less in being built and being operated on that grid than even a moderate embodied carbon building just in being made. So again, 50 years worth of operations is the equivalent of just simply making a building right now. So here's, you know, again, that building that I was just sort of raving about, the sort of easy to do zero embodied carbon building, again, has the same kind of result that in its code compliant form, so not its energy efficient form, again, over that 50-year life cycle, hasn't emitted as much as making the high performance version of that building with high emitting materials. So, you know, it's again, just sort of seeing the impact that you can have and that impact lasts on the scale of the next 30 years.
All right, so now we're looking at what if we take that same building and move it to Ontario? So this is no change except the emissions profile of the grid source. And all of a sudden, all those yellow bars get really, really small. And you can see now we're adding on this multi-pronged approach. We're not just looking at the performance of the shell, we're not just looking at the materials that go into that shell, and we're not just looking at the equipment within that building, but we're looking at the energy source context of where that and how that building is being operated. And as Chris mentioned, around the reduction of emissions based on the electricity source for Ontario, we see all those big yellow bars turn into small yellow bars. And so when we start cleaning up the grid to that degree, we see that these investments in front-loading carbon emissions in the embodied phase of our buildings, by putting that into materials in the pursuit of reducing the energy profile while the building is operating, right? So basically investing in high carbon releasing insulation to be able to create high performance buildings. If we have a really clean grid, that investment is not going to pay off. And so again, simply chasing the energy profile of the building does not immediately equate to a better building for the climate. And we have to take that full perspective of where and how and what is operating that building, and not just look at energy, but look at actual carbon emissions to see if this is an investment worth making, if we're using materials that are not carbon storage or carbon drawdown materials. And when we, again, sort of comparing across these different buildings, a sort of a moderate, kind of sort of normal, conventional code minimum building has significantly less emissions over 50 years, actually 50% less than the embodied emissions of that high performance building. And if we then look on the other side of that graph and we look at the storage building, it actually stores 75% of that same kind of conventional style building. And so just looking at the degrees of change and magnitude across these different building types, when those operational emissions go down because our electricity source gets cleaner, that really changes our strategies around how we go about developing our buildings from a climate response perspective.
Ontario, we closed down our coal plants 4 or 5 years ago. So basically the entire grid, and we'll get into the complications of this, it's nuclear, and it's then hydro, and then natural gas and wind in that order. But nuclear is the bulk of it.
All right, so we're going to talk about that. Hold on, we're going to get there. Yeah, so, and just kind of keep drawing this apart, like this is now actually how we start getting to net zero carbon buildings. So we said that we're going to find a pathway there, and this is the pathway. We kind of address it from all these fronts. We're looking at the performance of our buildings. We're looking at the equipment to run those buildings. We're looking at the materials to create those buildings. We're looking at the energy sources and their carbon emissions to run these buildings. And if we can approach from that multi-pronged, multifaceted, this is the life cycle, the complicated, the not the soundbite approach to getting to that, but there is a pathway forward that we've been able to find to not just get to net zero carbon, which we can do using just the conventional off-the-shelf materials, but even the code minimum building using carbon storing materials can get us to being a net carbon storing building by the year 2050.
So we're just going to take a second to look at a couple of case studies to kind of ground this a little bit. So we can do this now affordably, and we just wanted to launch into that a little bit. So the Teachers Union Building in Trillium Lakelands area basically stored 86 tons of net CO2, 2,400 square feet, and was done at approximately $208 a square foot. And so it's important to see this. It's a commercial building, zero toxins as well. So as Chris pointed out earlier, the red list chemicals go way down when you get into the carbon storing materials, which is an exciting stacked benefit. We're looking at net energy production on site, and again, the locality of the materials matters, and then looking also at the waste stream. The Zero House Project, which this was in 2017, and Chris's school, Endeavor, took this on. 1,100 square feet, $254 a square foot, stored 24 tons of CO2 in this building. And it was also a modular building, so exciting in that way as well. And again, we can see these host of benefits that are also ancillary and go within the project as well. Very important. This is the Unicorn Farm residence that New Frameworks did in Vermont, also in 2014. The square footage, 1,650. The cost is a little more. It was a pretty custom project. Lots of reclaimed materials, which was super cool and also very expensive to do, as you all probably know. But what's interesting about that number is that it was not the carbon storage in this building that drove that cost. It was rather the finishes and the choices of the owners. And then this building is off-grid, fossil fuel and foam free, and it stored 600 kilograms of carbon in 2014. So then also just thinking again beyond the numbers, like Chris was saying, we're looking at making these carbon storing buildings and these larger networks and systems like we've been talking about, creating this interconnected thinking and this interconnected way of working. So we're looking at the crew working directly with foresters and farmers in our region, connecting to those sustainable forestry and sustainable agriculture systems, looking at the renewable energy use on site, even during the production of the building, taking care of waste in a similar, responsible fashion where we're looking more at closing those loops, and then looking at the content of the crew. Who are the people who are doing the work? We'll get into this a little later, but everybody talks about how hard it is to find new people coming into the trades particularly. And one of my favorite things to talk about is that if we change the culture of the building trades and of the design trades, we will have a much broader range of people who are interested in joining us. So that's an important thing to look at as well.
All right, so I want to set up, we're going to put out a lot of ideas really quickly. And I want you to think of this not as things you have to hold on to and get really worked up about, but really, these are the framing questions for the conference. Yeah. There's a whole bunch of questions that were already coming up around, well, what about this, and what about that variable, and these other variables, and that's the risk we take in making this into a more of a comprehensive and integrated and holistic perspective. So we're going to go through a whole bunch of the questions that we have. You're going to have your own questions, and there is something, everyone in this room has expertise in one of these slides, and everyone is going to take interest in one of these topics. And I want to invite you to find the thing that interests you, make a note of that, and carry that with you for the rest of the conference and the rest of your work, and follow that path, because it's going to take all of us working on all of these issues to be able to get to that zero carbon by 2050. So we're going to start looking at how do we think about these different materials. And there's a few different categories. We talked about using recycled materials, and some of our storage materials are from a waste stream. Well, how large are those stocks? And how long will they be available to us in the case of, say, paper, if we're moving more to a paperless economy? What are the emissions of collecting and transporting those? Those were not revealed in some of our embodied carbon numbers. And what else would have happened to that waste? Is that storage actually count as storage compared to what else would have happened to those waste stocks? And looking at the agricultural residue, that is a big piece for us. There's all these different types of ag materials. What is the capacity of that? We looked at a number for straw, but not everyone has straw everywhere they are. So what are the ecological resources within your region? What's that capacity? We know that without caretaking the soil, we lose the carbon storing benefit. So it's not simply a matter of just grabbing the straw. We need to make sure that the soil that straw is grown in is well caretaken as well. So what are the management, the soil management and land management and impact practices of that agricultural industry? And what happens if we need to start devoting land towards growing building materials? And what does that look like for rural economies and for land use? If we're talking about factory-based materials, what kinds of factory inputs are going in there to make these biomason bricks or these mushroom foam boards? Are we okay using GMO organisms for those products if that's what's required to be able to achieve that? And how do we do that safely? And what does manufacturing look like now? Manufacturing has been tremendously disrupted. So are we looking at large centralized old school manufacturing structures? Are we looking at something decentralized or the next generation of smart manufacturing? And forestry is a big one. Those that we already have started like obsessing over what it means to count wood as a potential storage material.
And actually, if I can just jump in, none of those models counted wood as a storage material because the notion of does it count in wood is so fraught with so many problems. I just didn't count it. So I counted the embodied carbon emissions of harvesting the wood, but not wood as storage, except in the case of FSC flooring and FSC cladding, because it seems like that of that whole swath of materials are the ones that I can go find locally and have some notion that those practices are what they say they are, but otherwise wood was not being counted. So
whether we're looking at a genetically modified clear-cut plantation pine being trucked from the northwest, or whether we're looking at locally soil, preserved, multi-generational, long-term management practices in the Northeast, is going to make the difference as to whether that stud is a gainer or a loser for us.
Okay, there's also really important design strategies at work in how you go about approaching this too. So one of the things that wasn't really switched up very much in those models was the foundation. They were all, I think, concrete foundations. One had a rammed earth block foundation. So I was not looking at, can you change the whole design of the building to use less carbon? And one way of doing that would be to move to post foundations or pier foundations and basically get rid of all that concrete that's in the ground. But there are also all kinds of interesting rammed earth materials and new cement formulations coming on, but you could definitely change the profile of those sample buildings by actually changing the design of the building as well, and that wasn't really explored. The data and the transparency of the data, it was a hunt for me to track down all those EPDs, but that's starting to get better. There are more repositories of them. There are more of them coming out. There's a lot of work going on now to harmonize them to make sure that if you're looking at one done by this company and one done by that company, you're looking at the same thing. And more tools coming online to sort of put that information at the fingertips of a designer in real time during the design process. Switch out a material in your design and see the carbon impact right away. Making sure that right now designers and the sort of manufacturing world, there's a fairly big divide between the two of them, but I think one of the things that this offers us is for designers and builders to be involved with foresters and farmers, and to sort of not wait for somebody else to build these carbon storing products for us, but to engage with people who have those raw materials and try to help that come along.
We've done farm to table. We need farm to building.
Farm to building, yeah. And then there's a large question around end of life, the end of life, even of a carbon storing building. Eventually that building stops being a building, whether it's in 50 years or 100 years or 500 years. What does that mean? What do we do with the carbon that was in that building later? Can we turn it into biochar, in which case it's now stored permanently? Thinking a lot about composite materials. A lot of what people are trying to do with plants is mix them up with plastics. So you embody a bunch of carbon by putting it in there, but at the end of the lifespan of that material, like, what do you do with those weird composites, and is that a problem? And I think if we're going to ask policymakers to encourage us to make low embodied carbon buildings, these notions have to be built into those policies. Like, then there have to be rules about what do you do with the carbon at the end of the building's life as well.
And so then, a lot of the what and then more of the how. There are barriers to the carbon storing materials that are really important for us, actually critical for us to immediately grapple with, because we just saw how badly we need them. So we really need to grapple with these challenges. So affordability, there's a host of things to make sure. I mean, when we have a material that is not mass produced and is not currently being subsidized by our government, like the petrochemical industry, we are going to have different models for how to get these things to us in a way that is going to be affordable. Housing for climate refugees, so looking at human movement and what is resilient and regenerative housing going to look like really for all of us. I mean, the term climate refugee is sort of funny because we all are going to be one, so it's pretty key to lock that in soon and look at that. Replicable and scalable, so I talked a little bit about the training for existing workers. I mean, right now we need to get everybody going on this, and we also need to really look at who is coming into our trade and open it up to people who are non-traditional trades, people like women, people of color, folks with disabilities. It's critical that we need all of us to be able to tackle this problem. Open source sharing is critical as well. We need that best practices developing quickly. This is not about who can make the most profit on the best carbon storing strategy. Clearly we see where that will get us. We are trying to all work together to make this right. And as Jacob mentioned, the disruptive manufacturing is going to be key, and new methods of that. Existing buildings, we need to work with what we have. And it's challenging. It's challenging to work within a retrofit setting and figure out how to use carbon storing materials in that setting. So that's something we need to all, again, get to working on. Mitigating hazards as well, dealing with existing buildings. Many of you work in renovation and retrofit and know that we deal with lead, everything, asbestos, etc., and existing performance problems of those buildings. So figuring out how to do the Venn diagram of bringing all those things together and coming up with a solution together is a challenge. We're going to need each other. Codes and permits. So carbon pricing, again, these strategies that are going to help to show the true cost of what we're doing is critical. So that we don't have these false dichotomies of, oh, well, foam is so much cheaper, we have to use it. We don't have time for that anymore. And so we're going to need to really change these structures to be able to make this different. Policies to encourage innovation as well, and then greening the codes. So lots of work to be done with the codes to be able to update to what we're talking about and be able to make room for that.
Last topic of questions that we have involves the externalities, the things that haven't been counted, picking up on what Ace was just saying. And a lot of this comes from those uncalculated emissions. Now, Chris mentioned nuclear power is one of the things that makes Ontario's grid look so good, but I can be really confident that they're not looking at the embodied carbon emissions of mining and refining uranium or plutonium or whatever they're using to fuel those things. I'm looking at natural gas. There was a fantastic keynote a couple of years ago that looked at the tremendous tremendous amount of natural gas leakage that wasn't even accounted for. And the methane impact of that is huge relative to the impact of just a molecule of carbon dioxide. And that's not counted in these numbers. Neither is these massive hydroelectric reservoirs, where as they're rapidly cycling their water levels, and we have this repetitive growth cycle of plants that is constantly rotting, also releasing huge amounts of methane. That's not in these numbers either, and it needs to be, so that we can understand what we're working with and how to address these problems.
Or just to note, the indigenous people who are displaced in Canada due to hydroelectric dams. So like, you know, again, we're layering all of these social justice and ecological issues that need to be looked at together.
Absolutely. Can anyone guess what the #1 issue for Project Drawdown, that was this fantastic research project that lists like 80 some odd different materials or strategies for reducing atmospheric carbon dioxide? What's the #1? Refrigerant. So we are now putting tremendous amounts of refrigerant-based systems all across North America in the pursuit of reducing the operational carbon loading of our buildings. We need to know what we're doing with that refrigerant. How much is leaking? What's the maintenance cycles on those? Do we need to establish better practices and better oversight controls for the tradespeople and for the design practices around incorporating those refrigerant-based systems into our buildings? And are there alternate refrigerants? Can we move more quickly to CO2-based refrigerants to be able to still embrace that technology? And renewables. We know really pretty clearly that if you put solar panels on your roof, that does not mean you have a net zero carbon emission building. It does not work that way. The electrons do not get selected from the panels and put into your grid. We are still reliant on the ISO New England grid if we have a grid intertied system. And so those of us that are working on the grid side of things, renewables, storage on-site, utility scale storage, all of this becomes a really critical component of this. And understanding, if we're throwing a whole bunch of lithium at this situation, do we know what that impact is and how we can manage for that as well in the hardware and physical infrastructure of storage? Where do we go from here? We're almost there.
I think it was Michelle who said we have everything we need. And I agree with that. And so one of the things we need is each other. And you'll see that both of these are Nessie pictures. And we chose that on purpose because having each other in a professional community of praxis, it's like an education word. Popular educator Paulo Freire from Brazil, that is his concept. And what it combines is the concept of action or practice with reflection. And study or theory. And so this idea that we are going to essentially create an experiential learning cycle here, and I mean, this is what this community does. It's not a new idea, but where we act and we practice, and then we have a place to reflect and create theory and share that theory, and then go back and improve our practice and do it again and do it again. So that is essential. That's what we're going to need to do. And then community connections with many other diverse groups of people, reaching beyond our immediate professional communities. We need empowerment. So Chris was speaking about, the need to become a citizen scientist and do this research. We need to reinvigorate that idea. This is not, we cannot wait for somebody else to do this work. We all need to throw in and do this work now and take more democratic control of our resources as a part of that. So I'm really, I'm so excited that tomorrow is the Youth Climate Day of Action, led by Greta. It's so exciting. I mean, really what I can say about this picture is that, heroes are not born, heroes are made by our actions. And the reason that Greta is someone that we look up to and applaud is because she's behaving in a heroic fashion. And that's something that we can all do. We can all behave like heroes, and we all must and need to. So the climate crisis is real. It's upon us. And we don't need anyone's permission. We actually need bold action and conviction, and we need to make radical changes in our practice right now. So by taking this immediate action, every single person in this room can become a part of carbon drawdown and reverse the imbalance to the planetary carbon cycle that is resulting in climate change.
All right, so we're going to hit our top 10 things that we can do from this point moving forward into this conference, into our practice. Build with plants that build soil and rocks made from the sky.
Chris.
We need to fix what we already have because those buildings that already exist are our low embodied carbon buildings.
Yes.
We need to focus on where the materials come from and how we get them, which we've been talking a lot about in this session, and we need to do much more.
We need to focus on where our energy comes from and what is the true climate impact of our energy sources.
We need to do what we can with current technology and make better technology. So we can't wait for the next big fix. We're going to do what we do now while simultaneously doing better things.
We need to change the codes and educate everybody really, really quickly.
We need to learn how to count carbon, and we need to understand what those numbers mean and develop a collective sense of smell around carbon numbers.
We need to build relationships of mutual aid with people beyond profit.
And the triple bottom line mandate of the Building Energy Bottom Lines is a fantastic place to start exploring that.
And then build understanding of and relationships with the ecological and earth systems that we've been talking about today that we depend on, and that depend on us, honestly.
And we need to act with great urgency, tremendous passion, and abundant joy, because we're in this for the long haul.
Okay, so I'm going to ask everybody, we're just going to take a second after all that, have a pause. And people can either close their eyes or have them open, whatever you're comfortable with. But I'm going to read a vision. Okay, it's 2024. Does anybody, how many years is that from now?
All right.
People have been talking about 10, so I just want to say, or 2050, but we're going to we're going to talk about 2024, 5 years. Okay, it's 2024. It's March 14th today. We are here at NESE in this room all together. As we walk in the room and look around, we are each filled with a sense of thrilled accomplishment. Together we have turned the tides with our buildings, and with every building we have made or are making is storing carbon and is high performance. We've worked to change codes, supported new manufacturing and distribution of materials that are regional, and build up our local economies, neighborhoods, rural towns, cities, and rural areas. We have pushed for a cleaner energy in our grid, and we're getting there. We've set an example for the rest of the building, engineering, and design trades to follow. We have been the leading edge. We have all worked hard on how social divisions like racism, sexism, homophobia, and transphobia weaken our industry, and as such, we have made space for the greatest number of women, people of color, trans, and genderqueer people to be in this room. We have partnered with our colleagues in agriculture and sustainable forestry to mutually lift up our practices, stacking benefits, and exponentially reversing climate change. We have transformed our section of industry in just 5 years. We did it together with boldness, diversity of tactics, and clarity of vision and common strength.
Okay.
So how?
So the practical steps is we just all have to stop making that building on the left right now. The next building you make should not be that one. You can change to making this one right away, that's great. And if you can't do any better than that right now, even doing that is better than what's on the left. Make that building in the next 2 or 3 years. Make that your goal, that in 2021, all the buildings you make are going to be around that line. And when we meet here again in 2024, we'll all be doing that building.
And there are a lot of great resources available. There are trade organizations, there's advocacy groups, there's certifications that really value and count carbon. There's better and better tools available and more tools coming out every day. Databases of information, the resources are out there and they're growing. So we're going to end right now with a metaphor. And what better metaphors to use than that of a tree, given the contents and theme that we've been talking about. And so we're going to start with an olive tree. And people used to plant olive trees, not with the expectation of reaping any harvest within their lifespan, but for their children and their grandchildren's children to be able to receive the fruits of those trees, because that's how long it takes for an olive tree to come to fruition. And not only was it setting up those future generations with a marketable product, but it bound the community together, and it bound that culture to the land. And it created a necessity of a relationship and interdependence with the land. And I invite us to open the potential of our buildings to be like olive trees, to be able to support the 100th and 200th year of occupancy in harmony and in cohabitation with the resources that support the creation of that building in the first place. But I also invite us to think about being like bamboo and making buildings like bamboo. Because bamboo grows very, very quickly. And there's a wide diversity of different types of bamboo that grow everywhere from humid climates to cold temperate climates. And bamboo is very rapidly renewable. So after it is cut and harvested, it regenerates very quickly for another harvest and creates a huge amount of biomass from a very relatively small area. And so to that end, our actions must be fast. And we must be able to reap the rewards of the work that we do today, not in 3 generations or 1 generation, but within the next 5 to 10 years. And we need that diversity. We need everyone in this room now stands in a leadership position in your community and in your circle, because we need everyone who is not in this room as well to be a part of this movement. And that true diversity is going to be the key, because if it does not support all of us, it will not serve any of us. And that ultimately, to be able to continue this work, it is exhausting, and it is tiring, and it is overwhelming. And we have the incredible benefit of the rich and fertile soil of the Nessie community at our disposal. And if we plant the roots of our work and our practices in that soil, then we can look to each other and to this community to rapidly renew our will, and that we can move forward into this conference and into your work with tremendous passion and abundant joy. So thank you so much for being here.